Okay, hi everyone. So today we will start a new chapter. This is on link prediction. And as I mentioned at the beginning, the link prediction is a very important concept that is generally used not only in social network analysis, but also in other graph theory, graph mining kind of tasks, right? So, so before this chapter, we have already discussed, we have already come across some preliminary ideas of what is link, how do you measure different quantities of link, quantities of a link, right? We have also seen different link centric measures, right? Link I mean arranging links based on some ranks, right? And how link in turn helps adding more prestige to nodes and so on. Today what we will do, we will discuss, we'll take this thing further, and we will introduce a new problem definition, problem statement altogether, which is called link prediction. Okay, so as the name suggests, the idea is to basically you are given a graph and your task is to predict links, some links in the graph. Now I will discuss what do you mean by some links. I just intentionally made it vague so that you basically listen to the remaining definitions. So now let's assume that you have this kind of networks, and this is a friendship network, for example, Facebook friendship network, where you have nodes and nodes are connected via links, and basically the task is to recommend possible candidate friends for a particular user, right? So can we recommend this guy as a potential friend for say Sophia, right? Can we recommend David as a potential friend for Sophia? So whenever we in our Facebook login, we always see that a set of friends, possible friends, candidate friends always pop up, and those are kind of recommendations that are given by Facebook. Okay, now you may wonder how Facebook finds those users as potential friends of yours, right? It may also happen that some of the friends are of not direct contact with you, right? And some of the friends, I mean, you may not know, you are completely, some of the friends are completely unknown to you, right? So and then when you dig deeper into the relations, you may figure out that okay, this guy was a classmate of one of my best friend's friend, okay, something like that. Now and you may wonder that okay, 2-hop 3-hop neighbors in a graph might be enough to do all these recommendations, right? But this is not the case always. We'll discuss how do we do that. But essentially, this friendship recommendation, as I mentioned in this particular example, this is an application of link prediction. This is a case case study of link prediction. Similarly, in e-commerce service, right? So you say you open Flipkart or you open Amazon, right? You see that okay, these are the potential products that you can buy, you may want to buy, right? This is also a recommendation. This is a product recommendation to users, right? And essentially this is link prediction, because if you think of a bipartite network where you have users in one partition and items in another partition, and if a user has already bought some item, you can create an edge between them. So then basically the link prediction task is to predict that what is going to be whether there's a possibility that this particular user will be linked to this product. Okay, so essentially it is a link prediction problem in a bipartite network. Okay, I mean, you can also model it as a unipartite network, but in general this kind of product recommendation system is generally modeled as a bipartite network. Now in e-commerce service, in movie recommendation, for example, right, in Facebook friendship recommendation, in Twitter follower recommendation, and so on and so forth, any sorts of recommendations where you model the setup as a graph, right? You can basically pose it as a link prediction problem. Okay. So now these are the applications. Some of them I've already mentioned. On online social network, recommend friends to connect, suggest users or pages to follow. In e-commerce service, recommend products or services. This is also important for policing, for our law enforcement agencies to identify hidden groups of terrorists, right? Spot criminals in security-related applications and so on. In biology, it is very important, to predict protein-protein interaction structures. It may happen. It may be possible that you do not know whether a pair of proteins would interact in the future or not. You have historical data, and the historical data, you have not seen any cases where a particular pair of proteins have interacted before. But according to your model, it is highly likely that that these pairs will interact, right? So you can actually investigate what would happen in future, or you may also investigate why they have not interacted so far. Okay. It is also important for removing, say, spurious edges or say outlier edges. Okay. Predicting missing links, predicting new links, and so on. In citation network, it is also applicable for missing citation prediction. What happens sometimes is that when we scrape publication data sets, right? For example, you are scraping Google Scholar or you are scraping DBLP. What basically happens is that you will be redirected to the actual publication page, right? For example, you will be redirected to ACM page, or you will be redirected to IEEE page or Springer page, and so on, right? And then you scrape the data. But it may happen that you may end up missing some of the references of a particular paper because of the scraping issue, the crawling issue, right? So now if you have a better link prediction task, where the task is to predict whether this paper has cited this paper or not, you can fill up some of the missing citations. Okay. In fact, you can use link predictions for your possible potential research collaborations, right? For example, you have a collaboration network where users are scientific researchers and two researchers. If two researchers have collaborated together in the past, you can create an edge. Now, in this network, if you study the network, if you predict links, that would help you basically suggest some potential researchers whom you may want to collaborate with in the future. Okay. Now, these are many applications. Now, let's look at the temporal change that a particular network generally encounters. Now, what do you mean by temporal change? So far we assume that the network is static, okay, in the sense like node is not coming, node is not getting deleted. Similarly for edges, right? So number of nodes, number of edges are fixed. Okay. So what would happen if the network changes over time? Now, most of the real world networks like Facebook, Twitter, these networks are growing in nature, right? So you have some topology at time t equals to t0, and you have some topology at time t equals to t1, where t1 is greater than t0, right? So you see that there are, so you represent the graph at time t0 at g v comma e. V is a number of set of nodes and e set of edges, and at t1 you have g v dash comma e dash, where v dash is a set of nodes at time t1 and e dash is a set of edges at time t1, right? Now there are 5 possible cases, right? If you look at the changes of gt0 and gt1, changes between these two topologies, right? You can basically find out 5 possible cases. Case 1 is that let's look at the addition. Okay. Now say this is g0, gt0. Okay. Now if you only think of additions, what are the possibilities? A node can get added without any edge. For example, here you see node D has added, D is added, right? But D doesn't have any link. Okay. In this case 2, D is added, but D is also associated with 2 edges. So edges have also been added. Node is also the node has also been added, right? And the third possibility is that the node set is same, but the edge set changes because you see a new edge between B and C. Right now, these are three possibilities with respect to addition of an entity. Okay. Removal of an entity, it may happen that an edge will get removed. So as you see here, this this edge has been removed, the dotted edge has been removed, and it may happen that a node is being removed. If a node is being removed, the associated edges, all its associated edges will also be removed. So if B is removed, then this edge will automatically be removed. So these are the 5 cases. Okay. Now, when we talk about link prediction problem, now remember this thing very, very important, very, very carefully. So when you talk about link prediction problems, in fact, I have seen many research papers. While reviewing those papers, I've seen many cases where people, misunderstood the concepts and made wrong assumptions. So there are 2 kinds of problems in link prediction. One is called missing link prediction, another is called future link prediction. Okay. Missing link prediction problem is that you are given a static network. You are given a static network. Forget about the timestamp. You are given a static network, and basically your task is to predict whether you have missed out some of the edges in the network, right? So you say you have created a citation network out of your data set, right? But your data curation process may not be accurate. It may be noisy. Okay. So therefore you are basically taking help of link prediction algorithms to predict some of the edges which you may have missed out, and you basically want to make your graph complete, accurate. Okay. So now this is called missing link prediction. You are given a network, static network at time t. There is no concept of time actually here because it's a static network, and your task is to predict the links which have already been formed, right? But since you scraped wrongly, you are not aware of those links, and you want to discover those links. So missing link prediction. The second problem is future link prediction. Okay. What is future link prediction? In future link prediction, you are given a graph at time t0. Okay. And your task is to predict which edges will be added at time t1. Right. You are given a graph at time t0. Right. Your task is to predict which edges will be added at time t1. Okay. Now you now you may think that it may be possible that at time t1 some nodes have already been added, or at a time t1 some nodes will be added, right? And among those nodes, among the new nodes, some edges will be formed. Those edges you can't predict at time t0 because you do not know at standing at time t0, you do not know those new nodes which are going to be formed. Okay. If you do not know those nodes, then how do you know whether those nodes will be connected or not? Okay. So in general, what we assume is that in future link prediction is that given a particular time t0, and whatever nodes exist at time t0, can we predict how many additional edges will be formed among these nodes present at t0? What I'm trying to say is that let's assume that you have this network at time t0. At time t1, at time t1, this new node has been added. So then this is the new edge, and so these 2 new edges have also been formed. So your task is to predict these 2 edges, not this one, because you already know this nodes at time t0, and your basically task would be to predict these edges, right? Now, what mistakes that people generally do in this particular setting is that now think of it from from a papers point of view, or from a implementations point of view, right? How do you do that? So in general, what we do is that we we take a graph G, right, and we randomly remove some edges. We randomly remove some edges and we predict those edges, because we already know those edges have been formed, right? So our model should be able to predict those edges. So we randomly remove those edges, and our model's task would be to predict those edges which have been removed from the graph, right? So this is missing link prediction. This is not future link prediction, right? Why this is not future link prediction? Because if you think of it as a future link prediction, right, and if you assume that okay, at this time whatever network you have, right, some edges are missing because you have removed those edges and you want to predict it, but the remaining topology is known to you. And if you assume that this is the graph at time t1, right, it's a mistake, because some information some information has been leaked. For example, say you have a graph, as I mentioned, you have a graph at t0, right? This is your graph, and this is your graph at t equals to 1. Okay. Now, if you consider this graph and say if you remove these two edges, right, and your algorithm's task could be to predict these two edges, and you call it as a future link prediction problem, this is wrong. Why this is wrong? Because you are taking into account this node, you are taking into account this edge while doing the computation, right? But this node and this edge has been added at time t1. Those two things were not there at time t0, right? You see my point? So this kind of setting is called missing link prediction. But if you really want to solve the future link prediction task, you need to have a temporal graph in hand, right? And then only you can solve the problem. You can't randomly remove it and remove some edges and predict them while considering it as a future link prediction problem. That's wrong. Okay. And
needles in the haystack.
And why this is a difficult problem? Why this is sometimes called as a needles in the haystack problem? Because now think about it. If you consider edges which have already been formed as a positive sample, and those node pairs which have not formed any edges, right, as negative samples, right? So now you can easily pose this problem as a binary classification problem, where what's the task? The task is that you take a pair of nodes, right? You predict whether this pair of nodes are connected or not, right? If it is connected, then you say that okay, a link, a link will be formed, or the link, the link already exists, right? Otherwise not. So it's a binary classification problem. The problem here is that the negative sample, the amount of negative samples is huge. So if you think of all possible pairs, so you have NC2 pairs, right? You have NC2 pairs, and number of nodes is generally, number of edges is generally of the order of number of nodes, right? So E is generally of the order of n. So if you think of the negative class, you have huge amount of negative samples, right? Now, therefore, this is already an imbalanced classification problem, right? So finding among all the negative samples, so many negative samples, how many will form edges in the future, it is extremely difficult. Okay, therefore it is sometimes compared as a this kind of analogy. Now, link prediction methods, if you look at the traditional approaches, there are many good survey papers on link prediction problems, right? But in general, if you look at the taxonomy, you basically divide methods into three groups. One is some heuristic based model, the other one is probabilistic model, and the last one is some information theoretical model, right? So I will discuss the heuristic based models and the probabilistic models, right, in this chapter, and the remaining one, the information theoretical model, which is already there in the book, I will not cover here because this basically is a part of the advanced course. Okay, so again, before that, let's discuss the experimental setup for link prediction. I've already mentioned the difference between future link prediction and missing link prediction. Okay, I have also mentioned about the positive samples and negative samples. Generally, number of edges is of the order of number of nodes, right? And you have and you have NC2 possibilities of number of edges in the graph. So if you subtract this from this, right, you will see that all those pairs which have not formed any edge, they basically belong to the negative samples, okay, negative class. So generally, I mean, you can basically think of it as an imbalance classification problem. But what people generally do, people generally sample out some negative samples from the huge chunk and make it balanced, and then you then basically train them on. Okay, for example, if you have 1,000 edges, 1,000 positive samples, 1,000 edges, you basically choose 1,000 such pairs which did not form edges, and those basically constitute your negative samples. Okay, so now how do you evaluate it? Now, as I mentioned, this can be posed as a binary classification problem, but given a pair of nodes, the task is to predict whether this pair of nodes has already formed an edge or not. So you can use standard classification, accuracy measurement metrics like precision, recall, F1 score, accuracy, and so on. So you can create a confusion matrix like this. I'm not explaining this. I think this is known to all of you. So you can create a confusion matrix. You have true positive, true negative, right? False positive, false negative. And based on these quantities, you can measure accuracy. Accuracy is true positive plus true negative by all. You have precision, where it is true positive by true positive plus false positive. You have recall, true positive by true positive plus false negative, right? And you can measure F1 score based on precision recall. You can also measure something called true positive rate or specificity, right? Which is basically true negative by true negative by false positive. You have false positive rate, which is false positive by plus true negative. So specificity and true positive rate and false positive rate, these are important for another context. Sometimes what happens is that since the classification problem is an imbalanced classification problem, right, it may happen that you unnecessarily get a huge amount of accuracy due to this imbalance problem. For example, you have a test set where there are 10 such samples, and out of 10 samples, 9 are negative samples and one is positive sample, right? Now, if you predict everything as negative samples, your accuracy is still 9 by 10, right? Which is basically wrong, right? Because you are not able to predict this one, the minority one. Okay, so to address this problem, we all know that in standard information retrieval kind of setting, we use ROC curve, right? Area under the AUC is something called AUC, where you first draw the ROC curve, right? Receiver operating characteristics curve, and you basically calculate the area under this curve, AUC-ROC curve, right? If you do not know what is AUC-ROC curve, you can just read any standard material from Wikipedia or any online sources. What it basically does is that it basically plots false positive rate and true positive rate, and you get something like this, right? So if you get this kind of diagonal line, this is worthless. If you get this kind of line, right, and this is really a good example. So the more you see a flat line like this, the line which basically moves towards the border, right, the better the accuracy of the model. So you can use AUC-ROC. You can also use something called precision recall curve, right? In precision recall curve, now this kind of metrics are also used when when it's not a flat kind of classification. You basically have some ranking, right? And the entities are ranked based on some probabilities, for example, and you basically take entities one by one based on the probabilities, higher to lower, and you keep on calculating precision and recall. Okay, so as you see here, say for example, you have 10 samples, you have 10 predictions. You take the first prediction and see whether it's correct or not. Based on that, you measure precision and recall, right? And that would give you a point. Similarly, you take the second one. Now you have first and second. You measure the precision and recall and you plot it, right? So and so on and so forth. You basically plot it and you get a precision and recall curve, and this would give you better idea about the results. So this kind of things we generally use when we have the imbalance classification problem. So some of the evaluation, some unique problems that we face in linked predictions during evaluation is that oftentimes we it's very difficult to curate temporal data, right? Temporal network structure. So therefore, as I mentioned, what we generally do mistakenly is that we take a static snapshot, remove some edges, and we claim that predicting the removed edges is nothing but future link prediction, but that's wrong. Okay. The second problem is that sometimes we ignore the directionality. For example, citation network is a directed graph, right? Follower-following network is a directed graph. We basically convert a directed graph to an undirected graph, and then you predict all these edges. But this is wrong. Why? Because when we do that, when we remove the directionality, you basically are saying that the edge is symmetric in nature, right? But this is wrong, right? So you should also be able to predict whether the edge exists from A to B or not. The link direction prediction is also important along with the existence of a link. Okay. Sometimes the links are signed links or weighted links. We often ignore those attributes, right? And we basically consider an edge with weight 1 and an edge with weight 100 as similarly while prediction, but that is wrong. Okay. And the class imbalance problem that I already mentioned, right? Now another problem, not a problem as such, basically a mistake or a known mistake that people generally do, is that I mentioned, right, that how do you remove links? You remove links and you want to predict those links, right? How do you remove links? Now you can actually make it you can judiciously remove links in such a way that it would become very easier for your model to predict. Okay, what I'm trying to say is that let's assume that right, let's assume that there's a graph like this. Okay, and in your test set, right? So in your test set, what I already mentioned is that you need to remove some edges, and the task is to predict those edges, right? So let's say that you remove this edge. So this is A, B, C, D, E, F, G, H, I, right? So in your test set, you remove. So in your training set, you removed AB, right? And this is something that you want to predict. So this edge has been removed. You also removed AC, right? You also removed BE. Think about it now. So if you really want to judge the, the accuracy of your method, right? Any model can easily predict the link AB. Why? Because already ADBE is a part of a clique, right? A quasi-clique or a semi-clique, whatever, right? Now it is very likely that AB also exists, right? So if a model can predict AB, that's not a surprise. But it is difficult to predict the link AC. Why? Because if I remove AC, the link AC, now look at the distance from A and C after removal of this one, right? The distance of A and C will increase manifold if we remove this edge, right? So therefore, this edge is something which has basically connected two very far endpoints. Okay, so if your model is really good, it should be able to predict this edge. It should be able to predict this edge, right? Now think about it. So in a test set, what you do, right? You try to cleverly choose and remove edges like AB, BE, right? AE, which are easy to predict, right? And then you evaluate your model based on those edges, and you say that okay, my accuracy of the model is 90% or 95%, right? So this is wrong, right? So what I'm trying to say is that the test set selection is also very crucial while measuring the accuracy of a link prediction problem, link prediction method. Similarly, for negative classes, right? It is very easy. Say, for example, you have a graph like this, right? Now these are positive classes because the edges exist, and you removed it and you predict it. Now think of the same graph again, and the same graph again, and let's assume that you are taking the negative class, right? C, D, E, F, G, H, I. Okay, so one negative class is AC, another negative class is AH, right? So AH means this one, and AC means this one. Okay, and your model should be able to say that your model should be able to say that AC are not connected and AH are not connected. Okay, now it is very easy to say that A and H are not connected. Why? Because A and H are far from each other. But it is very difficult to say that A and C are not connected. Why? Because A and C are part of a kind of a strong group, right? So in your test set, if you do not consider AC, if you consider AH only, right, your model should be able to predict it very easily, and you can again claim 90-95% accuracy. So test set selection is very important, and that's something which people generally cheat in most of the times. Okay, so all right, so now we discussed the different heuristics based approach that we generally take for link prediction. These are some of the very old approaches that people used to take early days. So let's start with a very, now we're talking about link prediction. Okay, link prediction task, right? Methods for link prediction. Okay, so the simple way to do this, to solve this problem, is to just look at the neighborhood intersection. Okay, so there's something called common neighborhood. Common neighborhood Cn between x and y is the neighborhood intersection of x and y, right? For example, if you look at the common neighborhood of C and A, you take C's neighbors, which is AF, AF D, right? This edge doesn't exist, by the way. Okay, and you want to predict whether this edge exists or not. So what you do, you take C's neighbors, which is AF, D, and E. You take A's neighbors, which is F, D, and E. Then you see the intersection, right? Right, and A also have B. A also has B as a neighbor. So therefore, you see that the intersection is 3. Similarly, you look at the intersection, neighborhood intersection of other pairs, and you decide the threshold, and then you know if and then you rank all the pairs based on this threshold, and you basically say that okay, top 5 edges are basically positive edges, and remaining edges are negative. The top 5 pairs are positive pairs, and remaining pairs are negative pairs. Okay. The second one is Jaccard coefficient. The problem in the first method is that if one of the nodes is a hub node, for example, right? The hub node generally has a lot of neighbors. If one of the nodes is a hub node, then the intersection will automatically increase. Say, for example, you can easily draw an example. There's a hub node and there's a node with degree 1 or degree 2. The intersection will always be it is highly likely that intersection will always be the minimum of the degree of those 2 nodes, right? So generally what we do, and another problem is that common neighborhood doesn't have any boundary, any range as such, right? So therefore we basically take Jaccard coefficient, which is again simple, intersection by union. We take the intersection of the neighbors and the union of neighbors, and then we get the value. Okay, so again, for all such pairs, we get the Jaccard coefficient, we rank them, and we take top few pairs which have high Jaccard coefficient, and you basically consider them as positive samples. If you make it a little bit complicated, you can use something called preferential attachment model. We already discussed earlier, Barabasi-Albert model, but here you take it in a very easy way. We basically say that okay, if 2 nodes have high degree, it is highly likely that they should be connected. Okay, so because we know that nodes, because of the homophily nature, nodes with similar characteristics generally get connected. Okay, so 2 nodes with similar degree, they often get connected. Okay, so the preferential attachment with similarity between x and y is the degree of x times degree of y. Very simple. Okay. Now this is very important. There is something called Adamic Adar distance. Adamic Adar distance. Adamic, there are 2 authors. Adamic basically stands for Lada Adamic, who is currently at Facebook. She was one of the faculties in, forget the university. So Lada Adamic and her colleague, so they proposed this approach. This is very simple. The idea is that if you really want to measure the similarity between 2 nodes, you look at their neighbors. You look at their common neighbors. Okay. Now you look at their common neighbors and you see that whether these common neighbors, each of these common neighbors, if each of them is connected to other nodes or not, right? Let's assume that you have A and B and you want to predict whether A and B are connected or not. You see that A and B, both A and B are connected to X. A and B are connected to X, right? There is another pair PQ and PQ are connected to Y. So for AB, the common neighbor is X. For PQ, the common neighbor is Y, right? Now you look at the involvement of X and Y with the other part of the graph, right? If X is also connected to many other nodes in the graph, it means that X is involved with many other nodes in the graph. Therefore, in that case, X involvement to connect 2 nodes A and B would be lesser. On the other hand, if Y is not connected to other nodes or connected to say only 1 or 2 nodes apart from P and Q, so Y's involvement to connect P and Q together in the future would be high. It's very intuitive, right? Now think of it from your friend's point of view, right? Say for example, you have a common friend. So there are two individuals, A and B, right? They are not friends, but A and B have a common friend, mutual friend X, and X is a very strong friend of both A and B. X is not a friend of other people, other individuals in the graph. So it is highly likely that X will eventually connect A and B. On the other hand, if you see that, okay, there are again two individuals P and Q, right? They are not connected, but they are connected. They are mutual friends of another, friend of another friend Y, another individual Y, and Y is a friend of a lot of other individuals. So Y's involvement to connect P and Q in the future is lesser compared to the the involvement that I mentioned for X. Okay. Now how do you measure it? So measurement is very simple. You now for a pair of nodes X and Y, the Adamic Adar distance between X and Y is basically you take common neighbors. Now this one gamma X is the neighbors of X, gamma Y is the neighbors of Y. You take the intersection. So basically common neighbors, you take each of the common neighbors Z, right? And you basically take 1 by let's ignore log for the time being. You basically take, you see this formula, you basically take 1 by kz. What is kz? Is a degree of node Z. So it means that lower the degree, higher this value, and higher the similarity. Lower the degree, higher the value, and higher the similarity. So if your common neighbors are not connected to many other individuals, right, that means it would basically help you increase the similarity between the pairs. Okay. Now instead of just taking the raw degree, you take the log of degree. Adamic Adar proposed to take the log of degree in the denominator, but you can also take the raw degree. Okay. There are many other such metrics available. There's something called Salton index. The Salton index, what it does, it basically take the intersection, similar to Jaccard. You take the intersection of neighbors divided by not the union this time. This is basically degree of X, degree of Y. You take the multiplication and you basically take the root over. Again, different philosophy. There is something called half promoted index and half depressed index. The idea behind half promoted index is that if a node is connected to, if a node is a neighbor of a hub, right? If a node is a neighbor of hub, that is beneficial for the node. Right? Now look at the formula. Numerator is same. Numerator in both the cases, in all the cases, numerator is basically same. The intersection of neighbors. Right? But here look at the denominator. Mean of kx comma ky. Now if among x and y, if anyone is a hub, right? If anyone is a hub, we take the mean, right? That means the hub's degree will not be reflected because we take the mean. So the non-hub node's degree will be reflected here. So it is always good to have a hub, hub node as the neighbor, because the hub node's degree will not be reflected. So hub basically promotes you. On the other hand, hub depressed index, look at the denominator, max. So when you take the max, always hub's degree will be reflected here. Hub's degree will be taken here. Right? So and since this is the denominator, the entire value will be decreased because this is high. The entire value will be decreased, and here the value will be increased. Okay. So different times, depending on the situations, you take either this one or this one or this one. Right. Now let's look at, now these are some of the local metrics. Now let's look at some of the global metrics, global heuristics. Right. There's something called Katz score. The Katz centrality we have already discussed earlier. Now what is Katz score? The same idea. Similarity between a Katz similarity between x and y. Okay, is what? Is basically a to the power pxy. What is a to the power pxy? So AXY is the adjacency matrix, entry XY. You have the adjacency matrix and you have X, you have Y, right? You basically look at, the entry corresponding to X comma Y. That is AXY. What is A square XY? You multiply the adjacency matrix with itself, right? Right, and the entry at XY will indicate something. What does it indicate? It indicates the number of paths with length 2 between X and Y, right? For example, say this is X, this is Y, right? In A of XY would be 0 because X and Y are not connected directly. But A square XY would be 0, would be 2 because there are 2 paths of length 2, right? Similarly, A to the power PXY means, so the value of A to the power PXY, say the value is 10. It means there are 10 paths of length P between X and Y. There are 10 paths of length P between X and Y, right? So what we are doing here, for every path length, for path length 1, path length 2, path length 3, or path length infinity, right? So path length 1, this would be just AXY, original adjacency matrix entry. For path length 2, this would be A square XY. Now for path length 1, we take the number of paths, number of such paths, and this is the damping factor, alpha to the power P. Meaning, so as P increase, right now this alpha damping factor ranges between 0 to 1. Let's say this is 0.3, right? So when P equals to 1, this is 0.3. When P goes to 2, this is 0.09, right? When P goes to 3, this is even lesser, right? 0.027. So as you increase the path length, the contribution for that for those paths towards the similarity calculations will reduce because of the damping factor. Okay. This is simple now, and this is similar to Katz centrality. I hope you remember what is Katz centrality. We discussed earlier. Now let's look at let's look at the next one. It is called heating time. Okay, so what is heating time? So the idea behind heating time basically stems from the random walk behavior. Okay, so the similarity between X and Y in terms of heating time is the expected number of steps a random walker takes to move from X to Y. Expected number of steps. Why this is expected? Because this is probabilistic, right? Random walking process. Random walk itself is a probabilistic approach, right? If you have two edges coming out of a node, you either take this node, this edge or this edge, right? And you have different heating time. So now why this is minus? Because lower the expected step, higher the similarity, right? If someone takes 2 steps to move from X to Y versus someone takes 10 steps to move from X to Y, right? The first one is more similar, right? Therefore, if you take minus, so -2 minus 10, -2 is higher than -10. Therefore, you take minus here, right? Simple. Now, there is a similar metric called commute time. What is commute time? Now, here the idea is very same as random walk with restart kind of metric, but what it does here is that it basically says that you start from X, right? You move to Y, you reach Y, and you again come back to X. This is your commute time, right? So the commute time is basically heating time X to Y and heating time Y to X. And again you take minus. This is not same as random walk with restart Y, Because in random walk with restart, the idea was that at every node, you directly jump from that node to the initial node. But here it is not saying that you jump from that node to initial node. It basically says that you take a path and move from X to Y. You take another path and move from Y to X. You are not jumping from Y to X, by the way. You take a path and move from Y to X. Okay,